Okay, maybe let's get started. I'm recording, right? Okay. Share content. Okay, so, okay, not many people. Okay, so let's get started. So today we'll go over, chapter 23. It seems like he skipped some chapters, but it's going to be on power series. So let me sort of I'm going to have to go over ratio tests. So let me sort of review what lim sup lim inf is. So um, lim sup of a sequence an is uh, by definition limit n goes to infinity sup n greater than or equal to n. And so you could think of this as like a limit of like this sequence. So it's a limit of um, the sequence sup n greater than equal to of like this sequence. So sup n greater than equal to 2. So it's like a limit of sequence of sups. You could think of it that way. So sorry, there should be 3. So an example would be if an is -1 to the n, right? So in this case, right? So here, what is the sup of of n bigger than or equal to 1? So this is basically this term, the sequence an is what? When capital N is 1, it's -1, 1, -1, 1, -1, 1, right? So what's the supremum of this set? So this is, the sup of this set is 1, right? Now, now if I wanted sup n greater than equal to 2 an, well, this is like the n equals 1 term, right? This is n equals 2 term. This is n equals 3. So I want to take out n equals 1, right? So my sequence starts at 1 now. Starts at the n equals 2 part. And then n equals 3, n equals 4, n equals 5, and so on and so forth, right? This should be ... And the sup of this is still 1, right? And then so you can see that this thing, what's the limit of this sequence? It's 1, right? So, and then same thing for lim inf. So lim inf of an n goes to infinity is limit of the set of like infimums. Okay. So in this case, you could do for exercise, what you'll get is limit n goes to infinity of the sequence of -1s, right? Because the infimum of that set is always like -1. So, okay, any questions so far? Let me just check if, are people here? Okay. So, yeah. Okay, not many people. Okay, so let's continue. So again, we'll define f of x as some power series. So n equals 0 to infinity an x to the n. So this is power series an and r. So this is power series centered at 0. So for all n. Now, by definition, this is limit of the partial sums. So this is definition. So what we mean by this is we take the part, because we know what it means, what a finite sum is, right? So by infinite, it means just take the limit. So and whatever this limit is. So it turns out by root and ratio test that this thing either converges on all of R. So by converge, I mean the value, the limit is like a number and it's finite. So B converges at 0. So your power series always converges at 0, right? Because if you plug in x equals 0, like it's just an infinite sum of zeros, which is 0. So, and C converges on some bounded interval. On some bounded interval centered at 0. So the way you get this is either root or ratio. So main theorem, root test. So basically for series sum and x to the n, if beta is the lim sup, that's why I went over lim sup. So we all know what it is. So the lim sup of this sequence, and if we let R be 1 over beta, root test basically says if this is finite, so I power series converges for absolute value x less than R, and 2 power series diverges for absolute value x bigger than R. So again, the equal to R is inconclusive. And of course, this is assuming R is finite, right? So if beta equals 0, we sort of think of 1 over 0 as like infinity, right? And then if beta is sort of infinite, then we say R is 0. So R is like your radius of convergence. So if R is infinity, your series converges on the whole real line. And if R is 0, your series converges at the point 0. And here, and if you're here, then you converge on the interval negative R to R, right? And plus, I mean, it depends on boundary terms, but you'll have to check that. But yeah. So another test you could use is something called ratio test. So a series sum an of non-zero terms. One converges absolutely. So hopefully this is all review. So converges absolutely if lim sup of an plus 1 over an. So again, the lim sup comes into play, right? So in math 2b, they always wrote limit. And the reason for that is the problems in math 2b, like the limit tends to just exist. But if the limit doesn't exist, you can't really write limit, right? So you need to use lim sup or lim inf. So that's the reason here. So 2 diverges if lim inf of an plus 1 over an is bigger, bigger than 1. So note if the limit exists, it is your usual ratio test, right? Because if limit exists, lim sup is the limit, lim inf is the limit. So you could think, so the statement would be if the limit exists, converges absolutely if limit of your ratio is less than 1, diverges if limit of your ratio is bigger than 1. And 3, let me just write otherwise no information. Right. So these are mainly the two important, I mean, I'm sure you learn a lot of tests in Math 2B, but these two are probably the biggest ones. So something like, And then maybe in the another one is the statement, I'll call it star. If sum an converges, then the terms have to go to 0, right? Now, again, this statement is not very helpful, right? Because we tend to want to know if it converges, right? So assuming it converges, it doesn't really tell us anything, but the contrapositive does. So is it contrapositive? Yeah, contrapositive. So if equivalently, if limit n goes to infinity, an is not 0, then sum an diverges, right? So in order to converge, the terms have to go to 0. But note, it need not be the case that if your terms do go to 0, you could still diverge. But the thing is, it's just that if your terms don't go to 0, you immediately diverge. So in an example, so I'm saying not true if limit n goes to infinity, an is 0, sum an converges. Yeah. So this is not true, right? Standard example is sum 1 over n, right? So my an is 1 over n. It's pretty clear. Limit n goes to infinity, 1 over n is 0. But this is the harmonic series, right? And it diverges. So, okay, let me pull some problems from the book so we are all clear. So, let me go. What is this? Kenneth Ross. So we have, let me just pick 2 problems, right? Let's do 23.1a, right? So 1a, sum n squared x to the n. So basically how you would do this is you say, okay, I know that for any fixed x in R, what is this limit? If you think of x as a number, what is this limit? So it depends, right? Because here, if x is like a number between -1 and 1, it's going to go to 0, right? So you see here, a test for divergence doesn't really work. So unless you get, everything goes to 0, then you're golden. So here, let's use ratio tests. So let's calculate lim sup n goes to infinity. So here I need the n plus 1 term. So it's this x to the n plus 1 over n squared x to the n, right? So this is lim sup n goes to infinity. So this is n plus 1 squared over n squared, absolute value of x, right? So I took out the absolute value for the n, because if you square something, it's always positive, right? So in fact, n is always positive. So here, the limit exists, right? So the limit here is actually the limit, right? Because the limit of n plus 1 squared over n squared exists, right? So this thing is actually just the limit. So here, this is just 1. So the limit is absolute value of x, right? And what does ratio test say? Ratio test says, part 1, it converges absolutely if the lim sup, which is the limit in this case, is less than 1. So I need this to be less than 1. Okay. Now, here, it tells me I converge, right? So I converge on and then part 2, right? Part 2 of ratio test says I diverge if absolute value of x is bigger than 1, right? So diverge if. So what about, so what are we missing right here? We're missing equals 1, right? So basically need to check whether series converges at absolute value of x equal to 1. Well, what number has absolute value equal to 1, right? That's x equals 1, x equals -1, right? So here, basically, let's plug it in. So sum n squared x to the n, right? So for x equals 1, sum n squared x to the n is sum n squared, right? If I just plug in x equals 1. And here, this diverges, right? By what I just told you. The limit n goes to infinity, n squared is not 0, right? In fact, it's infinite. So by star, let me this is pretty important. By star, right? If your terms don't go, actually it should be but same thing. So this part. So if your terms don't go to 0, then you diverge, right? So here doesn't go to 0, so it diverges, and x equals -1. It will be -1 to the n. And what is this? Well, this thing, limit n goes to infinity, n squared. -1 always bounces between, -1 to the n always bounces between -1 and 1, right? But n squared is getting arbitrarily big. So in particular, it's not going to go to 0. So you see that it converges on like -1, 1. Okay, so hopefully you are all clear on this. So I'll do one more example later if we have time. So anyway, so let's do something more harder that's not Math 2B. So let's say 23.6, right? I noticed like Neil sometimes gives homework from the book. So, okay. Suppose some an x to the n has finite radius of convergence r, and an is bigger than or equal to 0 for all n. So 23.6. Suppose some an x to the n has finite radius of convergence r, and an is always positive, right? So basically, we need to show if the series converges at r, then it converges at -r. Converges at r, then series converges at -r. So why is that? So hopefully you all remember absolute convergence, right? So if a series converges absolutely, then it converges, which means if you take the absolute value on the inside, then if it converges there, then it converges in the original, right? So basically you want to check, does this series converge, right? Does converge. Well, sorry, converge. I missed that. Okay. So here, okay, there's a -1 to the n here, right? If I write this as, to the n, -1 to the n, right? So one way to get rid of -1 to the n's is take absolute value, right? So let's instead check whether this converges. So an, the absolute value converges, right? And this is what? this is what happens to the -1 to the n when you take absolute value. It goes away, right? So you get an r to the n. And we know that r is positive and an is always positive, right? So this thing is just this. And we assume it converged at r, right? So basically, converges by assumption. So that means this thing converges absolutely, right? So it converges. So hopefully you all remember this. So the harder part is the second part. So give an example of a series that, you know, doesn't, so here we converge at like bracket -r to r, right? So this converged at like both closed interval. So here they want something that converges on an open interval. So I need an an. So for part B, I need an an, right? Need an such that some an x to the n has property some an -1 to the n. So I want it to not converge at negative, diverges. But this thing, when I plug in x equals 1, it converges. So this is just an, right? Because I want bracket at 1 and open interval at -1. So I need it to diverge at -1, but converge at 1. Is there a series that, you know, rings a bell, I guess? So you can actually, you know, think of the most easiest series here. So the most easiest series here is just 1 over n, right? So what I suggest is do this, right? So here, if I just put an as 1 over n, it's the opposite, right? Because if I put an as 1 over n, some an -1 to the n will converge, and some an diverges, right? So it's sort of the opposite of what we want, right? So not what we want. We want opposite, right? So how do I flip it? Well, it's that -1 to the n, right? So we should let our an be this, right? If our an is this, some an -1 to the n is what? It's some 1 over n, right? Because -1 to the n times -1 to the n is -1 to the 2n, and -1 to any even power is 1, right? So this thing diverges while some 1 over n converges, right? So if you forgot why, it's alternating series test. So, okay, but hopefully that's enough of math 2B. But let's get on to like the important stuff. So you might wonder what, you know, so let me phrase it this way. We had f of x as a function, right? In terms of a power series. So a function in terms, this is the function. So I can ask, you know, ddx of f of x, right? An integral of f of x. You all certainly, you know, learned this, right? But ddx of this is some infinite thing, right? If let's say I started at 1, you might wonder, can I differentiate term by term? So in other words, can I swap it? So here it's can I just swap the sum and integral? And here you know what it is, right? It's power rule, right? I mean, like derivative of like x squared is like 2x, right? So this is an times n x to the n minus 1, right? Like just think n equals 2, then derivative of x squared is 2x. So you might wonder, can I just move the derivative inside and, you know, just take the derivative, right? So there is a partial step here. So remember, so recall that this is by definition. So by definition, limit n goes to infinity sum. So what you're really doing is swapping. The question is, can you swap limit with derivative? So here derivative of a finite sum is just term by term, right? Because, you know, I'm sure you all saw the rule, heard, like, you know, derivative of f plus g is f prime x plus g prime x, right? So here, this thing's finite, right? So it's certainly, you can certainly take derivative of a finite sum. The only problem is right here, you had derivative of an infinite sum, and that was a problem. So you could prove by induction, you know, the derivative of finite sum is just, so from here, you get limit n goes to infinity sum an times, right, which is just the top part, which is just this thing is just this thing. So I'm saying there are like steps in between. So like there are steps in between, but basically the question is, you could think of it like, can I swap derivative with the sum, with the infinite sum, right? And same for integral, right? If I had some like infinite sum and I integrate and x to the n, can I just swap it, right? Sorry, dx, there should be dx. And x to the n dx, right? Because this you know how to do, right? Again, it's gonna be an, you know, you know the formula, right? So it's given by this, right? So the question is, can you just, you know, can you just differentiate term by term? Can you integrate term by term? And it turns out inside interval of convergence, which is why we cared about, you know, finding intervals of convergence so much, is that inside interval of convergence, you can swap. Let me just write it that way. Convergence, you can swap. Okay, so let me sort of motivate the idea, yeah? So how about this? Let me try to more motivate, you know, the idea for the next section, because the next section will be the most important. So is the limit of continuous functions continuous? So if I gave you a sequence of continuous functions, let's say fn of x is cosine of x to the n, right? Certainly for each n, this is continuous, right? Like n equals 1, cosine of x is continuous. N equals 2, cosine squared is certainly continuous. Cosine cubed is continuous, so on and so forth, right? But is the limit continuous? Well, let's say, suppose x is not a multiple of pi, right? If x is not a multiple of pi, limit n goes to infinity, cosine of x to the n is what? So if x is not a multiple of pi, cosine is not -1 or 1, right? If cosine is not -1 or 1, it's some number between -1 and 1. And a number between -1 and 1, if you keep raising it to some power, it gets smaller and smaller, right? Like, for example, a half to the a half squared is a fourth, a half cubed is an eighth. It gets smaller and smaller, right? So this is 0. So now suppose x is even multiple of pi, multiple of pi. So what is this limit? So this limit is, well, cosine of 0 pi, 2 pi, 4 pi, 6 pi, it's 1, right? So this goes to 1. Now, suppose x is odd multiple of pi. Then limit n goes to infinity of cosine of x to the n is just negative 1 to the n, right? Because cosine of pi, 3 pi, 5 pi, 7 pi, that's all negative 1, right? And you know this limit does not exist, right? Because you're oscillating between 1 and negative 1, right? So negative 1 to the first power is 1, negative 1 squared is 1, negative 1 cubed is negative 1. So you just keep oscillating, right? You can't have a limit. So you see here, this is bad, right? Because all your functions in your sequence are continuous, and forget, is the limit continuous? The limit doesn't even exist sometimes, right? So you see that this is very bad. So basically, let me try to convince you more. So questions. So consider fn of x is 1 over n sine of nx. So clearly this is differentiable, right? You learned in math, I know we didn't go over derivative yet, but in math 2a, you know what the derivative of this is, right? 1 over n is a number, so derivative is like cosine of nx times n, right? You chain rule. So one thing to note is here, what is this limit? So this limit is 0, right? Because if you remember, one way you could prove this is sine of nx is bounded by 1, right? So this is bounded by 1 over n. And sine of nx is always bigger than or equal to negative 1, right? So this is bigger than negative 1 over n. And as n goes to infinity, both go to 0, so the middle term goes to 0. So this is 0 by squeeze theorem. And certainly, like, each of these are continuous, right? Like 1 times sine of 1 at 1. So this, when n is 1, is sine of x. When n is 2, is 1/2 sine of 2x. But it's certainly continuous, right? Each term. Now, what is this? So b, what is limit n goes to infinity fn prime of x? So the derivative is now what? The derivative is, hopefully you've done it, it's n times cosine of nx times 1 over n, right? So you have a 1 over n, and derivative of sine of nx is n times cosine of nx, right? You chain rule. So this is just cosine of nx. And we just showed above, right? Like, like right here, everything I did right here. Like sometimes the limit of cosine doesn't exist, right? So here, this thing might not exist, right? So for some values of x, I guess, and even and different value, and even if it did exist, one of them went to 1, one of them went to, like, 0, right? So this is a problem, right? Because you want, basically, the question was, can you swap limit with derivative, right? So is ddx, No, is it this? So on one hand, this side was what? Limit n goes to infinity, fn of x was 0, right? Derivative of 0 is 0. But on this side, the limit, might not exist, right? So that is a huge problem. So basically, I'm telling you, you might not be able to swap like limit and derivative all the time. And last one, so did I number this? No, sorry, I put question. So question, so fn of x, so each of these are continuous, right? For all x in 0, 1. These are brackets. So certainly if you plug in n equals 1, you get x, n equals 2 is 2x squared, n equals 3 is 3x cubed. These are continuous functions, right? So certainly limit n goes to infinity, fn of x is 0 for x in 0, 1, right? I mean, and then it diverges for, x equals 1. But for any number between 0 and 1 and 0, the limit's 0, right? Because you're taking powers of like numbers between 0 and 1. Like I said, 1/2 squared is a fourth, 1/2 cubed is 1/8, so on and so forth, right? So, but if you're not convinced, I mean, this is hard, right? Because you're multiplying by n. So if not convinced, let me prove formally that this limit's 0. So one trick you could do is consider this. Consider the sum n x to the n, right? Now, what does ratio test say? Ratio test. It says that lim sup n goes to infinity, n plus 1 x to the n over n x to the n. Sorry, this is n plus 1. If the lim sup's less than 1, it converges, right? So so here, this limit is, again, the limit exists. So the limit, let me just write limit, because we all know what limit n plus 1 over n is. The limit is, n plus 1 over n goes to 1, right? So this is just, this just means absolute value of x is less than 1, right? So basically, what this is saying is it converges on this interval, at least, right? I don't care about the boundaries right now. It could converge on the boundary, but I don't really care right now. The point is it converges, right? And what do you know about a series? So sum n x to the n converges on -1, 1. So if you go back to star, where's star? Right here, the blue underline. So this thing. If a series converges, the terms inside go to 0, right? So here my an is n x to the n. So since my series converges, my terms go to 0. So limit n goes to infinity, 0 for x in -1 to 1, right? By star. So that would be a formal proof. The trick is consider the series and then use ratio tests. But I don't even need -1 to 1, right? I just need 0 to 1, which is certainly included in -1 to 1. Now, the question is, can I swap, right? Integral fn of x dx. So if I take the integral, is this equal to limit n goes to infinity, integral fn of x dx? We calculated this side, right? We said that the limit, let me just write what fn is. So we are basically asking this, right? And, whoa, and x to the n dx, right? Is this true? And we calculated this part, right? Like up here, it's 0. And integral of 0 dx is just 0, right? So the question is the right-hand side also 0? Well, we can calculate this, right? What is this limit? What is the integral? If we integrate, I get x to the n plus 1 over n plus 1 times n, right? And, right, equal to 0. Sorry, on, this is integral from 0 to 1. Sorry about that. So what is this integral, right? So this integral is, sorry, yeah. So when you integrate, you have to evaluate, right, at the bounds. So I don't care about 0, right? If I plug in 0, 0, so I just need to plug in 1. And when I plug in 1, I get limit n goes to infinity, n over n plus 1. That is 1, right? So here you get 0 on this side, and this thing is 1. So it's not equal. So you see, like it's not always the case. You can just swap limits and limits with like sums and derivatives with sums, derivatives with, integrals with sums, stuff like that, right? So it needs some, there are some conditions. So here, all our functions were continuous, right? And we certainly like continuous functions because they satisfy stuff like IVT and like, IVT, extreme value theorem, stuff like that, right? So what's the issue here? The issue is convergence. Not strong enough. So basically the motivation is uniform convergence, kind of like uniform continuity, a little bit stronger, uniform convergence. Basically the motivation is it allows us to swap. So the reason we can swap for power series was that in the interval of convergence, our series converges uniformly. So basically, I'm saying this the limit of this sequence. Of course, I didn't define what uniform meant, but converges uniformly. That was why we could swap integral with sum and derivative with sum. But the motivation is the convergence is not strong enough. So yeah. So anyway, so for your quiz, so I decided to give 2 quizzes. Quiz 2 and 3 Wednesday. So quiz 2 is same, same. I upload, a file at 2:00 p.m. and then you do it. Quiz 3 is actually online. Everything is online. So quiz 3 is just math, 2B review. Yeah, so all the questions is just, find interval of convergence of this sum, math 2B, just questions on summation. So it should be easy because everything is multiple choice or true, false. Now warning, you only get 1 attempt and it's like, I forgot, it's like 15 to 20 minutes. So it will log you out after 15-20 minutes. So this thing, make sure you have stable internet and so on and so forth. So I think this is open for like, I think I opened it and for like, 2 days, I think. So something like that. So you have plenty of time to do it. So but you only get one attempt. So that's for quiz 3. So for quiz 2, the questions will be, I will ask on basically know the formal definition of uniform continuity. So by formal, I mean like epsilon delta, right? You basically your homework. So, and also know the definition, the epsilon delta definitions for limits in general, right? So know what it means to go to like a from the right of f of x, right? If it's some number m, like what if, like basically I might ask you to prove formally limit x goes to a from the left is, I don't know, is a number m, or maybe limit x goes to a from the left is negative infinity, right? So you have to know what the epsilon delta definitions for like x goes to whatever is number and infinite, right? And then maybe also limit x goes to infinity, right? What does this mean? So know like the epsilon delta definitions for these. And I guess again, I like giving just one true false question, or maybe some one example question. So give example of like a function satisfying some property, right? So I'm going to pull this out of the uniform continuity section. So make sure you study up on uniform continuity and I guess epsilon delta definitions for your quiz. But yeah, next time we'll go over basically uniform convergence. I'm guessing that's what the professor is going to do. So because that's a big topic in real analysis. So okay, any questions so far? That is all I have for today. So everyone good? Okay.